we have Bill, who's a principal data scientist with PyMC Labs. Bill will be talking about Gaussian process in practice with PyMC. So over to you, Bill.
This talk is about working with Gaussian processes in PyMC. So who here has done any work like Bayesian statistics work, like modeling? Oh, that's a good amount of people. Who's done it in PyMC or Stan or NumPyro? Something like that? Okay, a few more. Sorry, it's kind of ringing. Who's done work with like Gaussian processes before? 2, 1.5-ish? All right, so the point of this talk is to make that easier because Gaussian processes are great and they're very useful. I use them all the time. We use them all the time at PyMC Labs for work. And yeah, they're great, handy things. So I'm just going to speed through some of the first stuff that people mostly know and then try and spend a little more time on how to actually kind of use them in practice because they're sort of, they're really useful, but they're hard to get to work once you actually start getting into it. So, you know, they're great in theory and they're non-parametric. So you can use them to represent unknown functions without having to design them with parametric pieces. So I think that GPs are actually the ideal ML model. I'm going to be a little controversial, right? They give well-quantified uncertainty. You can specify them in terms of this thing called a covariance function, which means you're thinking more about how similar, you know, different input x values have to be to produce the same sort of y values, which is a lot more natural than, you know, the number of tree leaves or the number of hidden layers or neurons or whatever. So they're handy also for like including in regressions, modeling time series, other things like that. And they kind of sit, if you're going to place them, in this overlap of the Venn diagram between statistical modeling and machine learning. The problem is that they're really slow. So their computational complexity is order n cubed. So they're great, and everybody would use them all the time if it weren't for that, right? Just a small problem. So how this talk is kind of ordered is it's kind of going to go all over the place because GPs sit on top of a lot of other things. So I'm going to go really quick through what Bayesian statistics is, what a hierarchical model is, and then that'll lead into what a GP is, and then how to use them in your model. And that'll also kind of show by working through all that stuff when it's a good time to use it. So Bayesian statistics. I think it's probably better to call it Bayesian modeling, right? Because what you're doing is you're taking whatever kind of process you're trying to represent and then putting probability distributions around it. And that, kind of working through that, and that gives you uncertainty and estimates of parameters you don't know. So the sort of 3 ingredients you're going to have is some kind of process with some randomness in it. You know, you have noisy data of some sort that you think is going to be able to teach you about that process, and you have unknown parameters that inform how that data was generated. So, you know, day-to-day work, right? And it all kind of sits on Bayes' theorem, which I'm sure you've heard of. And it's the term on the left is the posterior. On the right, the top left is the likelihood. Then the prior to the right of that, P of A, and then the denominator, P of B. And we only care about, usually, the top part of that, the posterior. And given some data, D, this is kind of the likelihood part, what's the posterior distribution of our unknown parameters, theta? So what you need to do is define your likelihood. So this is sort of your data generating process, what the distribution of your data is, given if you know all the values of the unknown parameters in your model. Then you define your priors, P of theta. Theta can be one unknown thing, or it can be a lot of unknown things. And then the next step is you draw a large set of samples from the posterior, P theta given D, and that's what you're actually going to do your work with and figure things out. So this example that I'm going to use to kind of go through the whole talk is based on baseball. And I'll talk a little bit more about it as we go. But to start with, here's just a simple example of a simple Bayesian model just from start to finish and what you get. So at the end of the season, we're playing t-ball. We've got 2 hits out of 5 at-bats. What do we think that kid's batting average is going to be? And yeah, okay, I realized while I was doing it that you can kind of always hit the ball with t-ball, but anyway. So what I'm going to do is make 2 different priors, and we're going to solve this problem using the probabilistic programming language PyMC. And yeah, a batting average with 2 hits out of 5 at-bats, this is overkill, for sure. But we're starting really easy. So here's 2 priors, and I'm just plotting them here to sort of show some of the options that we could do. So the first prior is uninformative, right? We're saying that it's equally likely that at the end of the season, the kid has a batting average of 0 and 1. And actually, again, t-ball, it's probably 1. But for real baseball, we all kind of know that it hovers around maybe 200, 300, 100, that area. So that's what prior 2 is supposed to represent. It's more weakly informative, is what you'd call it. So we're not stacking the deck too much, but we're using some of our knowledge to inform what the answer is going to be, which is a reasonable thing to do when, if you already know it, then you already know it, so you should include it in your model, right? So here's the model in PyMC with some printing things, but it's really easy. The first line is just, well, the first line's the context for the model. The second line is your prior. So alpha 1, beta 1, that's the flat one. Then the next line is the likelihood, and then the third line is the sampling. So each line corresponds to the 3 steps I mentioned a couple slides ago. So you'll see n is 5, we observe 2 hits. And here's the result. So the posterior is in that cyan color, and it's in front of the prior. So you can see that the amount of information in 2 hits and 5 at-bats is exactly this much to kind of hone in on the batting average. So you get a better estimate of the uncertainty than if you just would have done 2 divided by 5 and called it good, because that's not a lot of at-bats, so you're going to have a lot of uncertainty. Now let's run the same thing again, but with a different prior that I used. So that's that first line. The only thing that's different is that alpha is 1.5 and beta is 3. So here's the answer now. And you can see that changing from prior 2, it's a little more peaked than you can tell. Before, it was over 0.4 pretty exactly, and now it's actually a bit to the left of that, so more towards 0.3. So, by taking this Bayesian approach to modeling, I'll flip back really quick so you can see the difference. See, this is more up, and this will be more a little to the left of that. So by taking this approach, you're able to both get well-quantified uncertainty and be able to incorporate your prior knowledge about the problem, whether it's from other experiments or existing data, into the problem you're trying to solve. Or you can just use it to constrain parameters, right? If you just know that something's positive, you just put a prior on it that doesn't have any mass over things that are negative, right? Which is also what we're doing here. Batting averages are not going to be a negative number. So if you're uncomfortable with including information, you can at least use priors just for that. So yeah, there's the summary. But oh yeah, don't use priors to stack the deck to get the answers you want. That is bad. All right, let's try and move towards a more realistic problem. So it's known in the baseball analytics world that player performance in terms of SLG, which is slugging percentage, tends to peak at age 26. So the SLG statistic, it's just like batting average, but it factors in hitting power by counting doubles and triples and home runs as 2, 3, and 4 instead of just 1 for a batting average, which is hit or no hit. So what we might want to learn is what does this curve look like? How fast does it rise and drop off? And then how certain are we about this curve anyway? So the rest of the talk is going to be about getting there and going through what we need to know in order to make this analysis happen. But in order to do that, we need a few more concepts. So we need to know about hierarchical modeling, and we need to know about, well, GPs, obviously, and then how GPs are sort of a more general case of a hierarchical model. So I'm going to kind of go through that trajectory. So hierarchical modeling. One strength of the Bayesian approach is how natural it is to represent hierarchical structures in your data. There's other ways to do it with other things, but it's kind of tricky. But in the Bayesian sort of context, it's really straightforward. So this next example, we're going to work up and start with batting average, just with one team, and then we'll move to SLG and do the age thing. It's kind of funny. If you just use average, this age effect doesn't really quite pop out, but it really does with the slugging percentage. So, okay, how is this problem hierarchical, estimating the batting average of a bunch of players on a team? So how it is you assume all baseball players on a given MLB team are drawn from the same distribution, right, which is that team. You could estimate each player's average individually, like we just did with that one T-ball example. That's called no pooling. You're not pooling any information from other players. We could lump all the at-bats and all the number of bases total for the whole team, and that's complete pooling. So that's as if you just sort of total everything up. It's like one player, and then you just calculated it to get your team average. And that doesn't give you estimates for each player. Or you can do something that's kind of in between, which is players are drawn from a team distribution. So this makes sense because we know that everybody on an MLB team, they're Major League Baseball players. They're probably pretty good. So that's sort of the hierarchical structure, and that's called partial pooling. So here's some data. This is from 2023, and we're looking at the Dodgers because they won the World Series, right? So 2023 because I didn't get new data. But the following example is at-bats instead of SLG, and here's what this hierarchical model looks like in PyMC. So this first bit at the top is we're making the indexes for the player and then the player labels. That's called the coordinates, so we can include that in the model so that all of our parameter estimates have nice labels on them. And we have an intercept, which is like the average for everyone, and then sigma player, which is going to be the between player variance. So this is sort of like how different players are from each other. And that's going to be informed by if one player is really good and they have lots of hits, then they're going to have more weight because you have more data. And if another player is kind of bad and they don't get a lot of hits or their average is low, like the amount of variance across players is what sigma represents. And then the last thing is the logit of P. So P is just the batting average, the probability of getting a hit. And and so we'll calculate the batting average like this. We'll draw samples like that, just like we did before. And here's what we get. So we get estimates for each player. So you can see that, we're a lot more certain now because this is a whole season. This isn't 2 hits and 5 at-bats. So our posterior distributions are a lot narrower for each of the players. So you can see that, Shohei Ohtani and Mookie Betts have really similar batting averages. If anything, maybe Mookie Betts is a tiny bit higher, but we probably need to collect more samples to estimate these tail probabilities better. But the mean is probably estimated really well with the number of samples I drew. But then, interestingly, Jordan Adams also gets estimated a mean of about 220, which is interesting because in the data he had 35 at-bats and 5 hits. And if you directly calculate that, that's 0.128. So because he played for a short amount of time and then got injured, using a hierarchical model, we would forecast, it's like forecasting his end of season average. We would forecast this estimate to be quite a bit higher, just because he made the Dodgers, right? Which is a reasonable thing to do sometimes. So one thing we sort of assumed without talking about was something called exchangeability. So if we look at this and then remove it, this is what takes us from hierarchical models to GPs. So in the previous model, we treated every player as if they were exchangeable, right? It didn't matter if we changed the order. We didn't know anything about them other than they were just a player on the team. So, but what if, we know a little bit more about it and we're interested in the age, right? All the players have different ages. So once we include this and want to model it, right, now they're not exchangeable anymore. So what we really want our hierarchical model of player to do is to partially pool information more over players that have similar ages. Does that kind of make sense? So instead of just pooling them all equally, we want Jordan Adams to be pooled more closely with players that have a similar age, and the same for all the other players. And we can use a Gaussian process to accomplish this. That's one way of thinking about them. And we'll do the whole general what's a GP thing, but I think to me this is the easiest way to sort of lead into it. To see how we can get there, we can rewrite our model using a multivariate normal prior with a diagonal covariance matrix instead of a vector of IID normals for the player effect like we just did. So that's this. So this is the exact same model, actually. It's just written a little bit differently. You can see in the middle here, it's this part. So now we have this covariance matrix, which is diagonal, and we just take the sigma player value and put it on that diagonal. And then we're using a multivariate normal, and we don't have to. It's exactly the same as using a normal. And you would think, oh yeah, so I should say, just in case anybody hasn't seen it, multivariate normals, GPs, they're related. This is important. Kind of have to put this up here, is that we need to compute this thing, right? But if you'll notice on this slide, there's this import at the top, import pytensor.tensor. So pytensor is really cool. It's what backs PyMC. And it doesn't get nearly enough attention that it deserves. So this talk isn't about pytensor, but I just wanted to sneak in a couple slides to just so people know what it is, because when you're writing a PyMC model, you're like, oh, pytensor, it looks like NumPy, and then you start writing stuff, and then it's kind of not like NumPy, and it's kind of confusing, right? But it's very cool on its own. So what it does is it creates a symbolic graph of your computation, kind of like SymPy, and like TensorFlow 1. It actually started as Theano, like 20 years ago, something like that, a really long time ago, before I think the Theano people went and created TensorFlow. But Theano's been alive, and it's kind of been kept alive by PyMC, and then it became Asara off of a fork, and then it became PyTensor, which was a fork of Theano then. But it automatically applies rewrites too that makes your computation really fast. And another thing that it can do that's very, very cool is it can compile that computation into different backends. So right now, there's a C backend, Python, JAX, and Numba. And I think people are adding MLX, which is for Apple Silicon. So if you have those fancy M whatever chips, you can use that to run your code on, which is great, which will kind of keep it alive for a long time, because you can just add a new backend, whatever the coolest, newest deep learning framework is. And it also, which is great, is it allows you to manipulate the graph in a transparent way. So this is used by PyMC's do operator. And here's a quick bit of code that shows this rewrite. So if I go back really quickly here, you'll see we made this covariance matrix, multivariate normal. To solve this, remember the whole don't invert matrices, use some sort of decomposition and use solves, right? Well, here's the PyTensor code to do this, and you'll notice I just invert it. and then I multiply it. So this is sort of a multivariate normal-ish calculation to look really simple with the same way I set it up before. Here's what the graph for this looks like, right before PyTensor optimizes it. You can see what this is. There's a matrix multiplication, that's this guy, between mu and the matrix inverse. So this is just sort of directly calculating it. After PyTensor rewrites it, you'll notice that's all gone, right? Because it's a diagonal matrix, the Cholesky of it's diagonal, you don't have to do any of that stuff. You can just calculate it in a really simple way. The graph doesn't really look simple. It's kind of long, but you'll notice there are no inverses, no solves. I don't even think it's like there's a matrix multiplication left because you can just, well, maybe there is. Anyway, and so the calculation is actually just as fast as, or maybe similar to what we were using before with just the vector of IID normals. And we didn't have to do anything special. You can just write PT linear algebra inverse of something, which is very cool and very handy if you're trying to prototype some new algorithm. So back to the talk. So we're running a model where we used a multivariate normal with a diagonal covariance to represent the player effect instead of IID normals. And we wanted to see if we get the same result. So we can use GPs then when we don't think the covariance matrix should be diagonal, when the different ages are more related. That's what that's about. So here's the sampling, and here's the result, and it's the same, right? So we get the same answer. And so this gives you the same result as that. So let's try that. Let's actually make a covariance function that does this. And so what's a GP, right? I'm sure you've all seen this definition. A Gaussian process is an infinite collection of Gaussian variables, any finite subset of which has a multivariate normal distribution. So if it's infinite dimensional normal, right? That makes sense. I think it's easier to think about it because it's it's infinite dimensional in the sense that it's parameterized with a covariance function and not a covariance matrix, right? So this covariance function is lazily evaluated over your data. That means if you have 10 data points, you'd fit it as a 10D multivariate normal, but you can evaluate the GP over other x's later. So the dimensionality we're talking about isn't the dimensionality of x, as if x is like a 1D time series, or it's a 2D spatial model, or a model with features. That's not the dimensionality we're talking about here. It's over n, the number of data points, right? So if you have 10 data points, it's a 10D multivariate normal. If you have 100 data points, 100D multivariate normal. And then later when you're doing forecasting or interpolation, that's when it's sort of like infinite dimensional because you can evaluate it everywhere. So you can think of it as just a multivariate normal that's lazily evaluated. So that part is the downside, right? That's the n we're talking about where it's order n cubed. So as your data set gets big, these things get slow. So here's an example of an n, in quotes, dimensional GP over 2 input dimensions. So 2D, it's like, you can think of these as lots of time series moving left to right, and then moving forward, from back to front. That could be like different time series that have some sort of relationship. So that's why you can kind of see the smoothness across that front-back dimension in this picture here. So this is x is 2D, but the GP itself is infinite dimensional because you can evaluate it at any point in t, and there's infinite points along t. Okay, so 2 important things to know up front when dealing with GPs. And the first one is that you usually need to use approximations, right? So they're still just GPs, but they'll have sort of different names. One we use a lot in PyMC is HSGP. That one's handy, and there's a ton of other ones too. But the other thing is that you need to be really mindful and careful about how you're setting priors on the GP hyperparameters and what those hyperparameters do. And there's a lot of information out there about the first one and sort of when to choose which approximation. And in my experience, there's not a lot of information about the second, and that one is just sort of learned over time and maybe from here or there picking up little bits. And so this talk is going to be all about the second thing from here on out, which is kind of what you need to know every time you do a GP problem also. And sort of, I hope that once we go over this, that working with GPs becomes quite natural and pretty smooth. And not a lot of time is spent on, I fit it, now it doesn't work, delete it, you know, and go back to splines. So with baseball, we need a covariance function, right? That's sort of the main ingredient in GP. We had this diagonal thing, but that wasn't really a function. And we need something that like operates over age and returns a larger value, a larger covariance, if the players' ages are similar. So that's what this function does here. It's called the exponentiated quadratic covariance function, and the reason I'm showing it is because it has a nice simple form. So if the x's are closer, this thing equals eta, and if the x's are really far apart, then it goes to 0. So the length scale is really the important parameter. That's this L down here. It controls what you think of as similar. So the age here in the baseball example is measured in years, right? So if L is 10, that's like decades, 100 is centuries, and if it's really small, that's like minutes or seconds or something even smaller. And that is totally irrelevant for this example. The data is not that granular, and we don't care. So here, close might be 1 year, maybe 5 years, right? And this length scale is fortunately really interpretable. And so we'll be able to set really informative priors on it. And I'll kind of show later that it's actually really important that you do that in order to get these things to work. So there's a lot of functions, you know, this goes to show too, right, that there's a lot of variation that a GP with this covariance function could represent. Like the space of functions is huge if you're allowing L to be anything. So here's an example with a length scale of 2 with the ages going from 20 to 30. So this kind of says that like when the length scale is 2, it's like this is sort of how it tapers off with players that are like 0 years apart along the diagonal, and then 1 year, 2 years, 3 years working down or working across. And this is more to just get a feel for it, making a picture like this, how the partial pooling is going to actually be happening in your model. So yeah, let's look at the limiting cases. That's really helpful for seeing what this thing does. If we push the length scale to 0 and then to infinity and see what happens to these functions. So the length scale goes to 0, right? You kind of simplify this, and you end up with the identity matrix again. So this is exactly the same as when we just use the multivariate normal. So when the length scale goes to 0, we're just back to a regular hierarchical model. And there it is. And so if the length scale, also the other point is if the length scale is smaller than the resolution of your data, you're going to have identifiability issues. That means that when you're changing the length scale and you're below the resolution of your data, nothing is actually changing in your likelihood or your posterior. And so the sampler is just going to kind of meander around there in this flat space, which isn't helpful. So don't make the model try and do that, right? And then here's a sketch of that happening. So you can take some random numbers and then kind of use the same random draw and then smooth it out as if it were a GP, and then kind of work from a large length scale, which is the lighter color, down to a small length scale. And you can see that the way it changes is you have this, these are the random numbers in black, and then you smooth them out, and once the length scale gets small, you'll notice it doesn't really change that much. Most of the change happens when you're moving from large length scales to smaller, like visual change, right? And so you can kind of think of the length scale as like a smoother. And the amount of smoothing isn't equal as the length scale changes, which is important to keep in mind too when you're doing this. So the fix, right? So what you always have to do, you can kind of like check this box when you're fitting with GPs, is you need the length scale to block, like you need your prior to block small length scale values. and especially always those below the resolution of your data. So some priors you could use are these four. And this is what those four kind of look like. And you'll notice all of them kind of drop to 0 here, and they all have kind of long right tails. And we'll get to the right tail part of it next. But the two I use the most are PC priors and inverse gammas. The PC prior, if you look back, that's the one in black. That's the one that has the longest right tail. And you use it when you want to allow for the possibility that the GP could just learn a flat line. And we'll see that next. And the inverse gamma is nice when you want to be the most informative, because it has a long right tail, but it's not that big. And it's very good at squishing that early part of the space, of the prior space, yeah. So here's the case then when the length scale goes to infinity. When that happens, the covariance matrix just becomes a matrix of all ones, actually. This looks a little strange, but it's possible to draw prior samples from a GP whose covariance matrix is all ones. And they're just flat lines. Not very interesting, but it makes sense, right? Because that just means that how similar, like all the x's are completely similar, so all the y's have to be exactly the same. There's no difference from age 10 to age 11. It's the exact same covariance all the way across. So the only sort of answer to that is just flat lines, right? But this gives you identifiability troubles when your length scale gets too big then, because that's the same thing as an intercept, which is probably in your model already. And so then your intercept and the GP start kind of fighting with each other and causing the sampler to bog down and not really converge properly. Or you'll get, yeah. Anyway, so in the next sketch, you can see what happens here. So in this case, we start with something, a small length scale, and then we keep increasing it. And you can see that once it gets really big, too, like I'm increasing by thousands up here, it's smooth, and it gets a little smoother and a little flatter, but most of the change is, again, happening at these sort of medium length scales, which, again, goes to the point that, you know, the amount the curve changes visually is not like the same as your amount that you're changing the length scale by. So the fix for this is mostly to just know that this might be happening and check for it. Some things you could do, practical things, is remove the intercept term from your model and just have the GP. Or remove the GP, because if it's trying so hard to be flat, then maybe nothing's there. You can also constrain the GP to have a mean of 0, which would just put it at as like a flat line at 0. And then how you kind of do that depends on the type of GP you're dealing with, and I won't go into that, but just know that's where you can look. And the other thing you can do is constrain the length scale to not be too large, which I kind of hinted at before by using something like the inverse gamma instead of the PC prior to tamp that down. So another thing, this is more detailed, but one thing you'll see when you're fitting these things is that the data usually isn't very informative of both the scale of the GP and the length scale. And this is why, for these types of covariance functions I've been talking about. And the reason is when you look at something called the power spectral density of the kernel, the scale and the length scale kind of just multiply each other here in the coefficient in the front. And that means that if you're trying to estimate these parameters, the product's identifiable, but each parameter isn't going to be. And so you'll often find that your GP itself, the line or whatever you're fitting, can have a pretty tight, can have a pretty like narrow posterior, but your posteriors on these parameters aren't going to be well informed. And so the posteriors will be wide. And so the reason that's important to know is because since those are going to be wide, it's more important to use informative priors on them, right? Since the data isn't just going to learn them for you really well. And the other thing is the more, we're all sort of used to the idea that the more data you collect, the lower your uncertainty is going to be. And that's not necessarily true for GPs. in order to get a narrow posterior around something like the length scale parameter, you need to see a lot of like zero crossings in your data. So for example, if this is what you're trying to fit and you only observe the sort of white area, it's going to be, you don't know what the length scale is. You just know it's long, right? But if you were to observe everything in the dotted lines, then you start to get a sense of it because you see it go up and down a few times. And then you can start to pin it down. So let's just zip through the baseball example again. And when we use this, if you don't know that stuff, this will be difficult. But if you do know it, this is pretty easy to do. So now we have data on multiple seasons from all the players on all the teams. And here's an example of what that looks like. So we're back to trying to estimate that age curve using like players' ability to have a high slugging percentage as a function of age. So I'm not going to include the model in the slides because it's like kind of a lot of code, didn't fit. But what's in the model is, in order to make age pop out, we need to regress out a few other factors. So the first one is the team. So players, teams play in different home parks, which have different shapes, and some are smaller than others, and it's easier to hit home runs and stuff. And so players on those teams are going to have higher slugging percentages. So we'll use a hierarchical non-GP term to represent the team. And then the player, of course. The biggest determining factor for slugging percentage is the player, obviously. And so we use a hierarchical term there and add our age GP to it. And then the season. So apparently, the balls used each season aren't going to be exactly the same. And there's like an effect you can spot where, like from juiced ball years, where there's more hits and stuff. So, or more doubles, more triples. So I'll make the code available on GitHub with like a repo with the talk and to run through it and use it as an example if you're doing work on this, or if you're trying to use GPs in your work. So just as a sample, here's just the intercept and the team effect from the model. And yeah, so the only sort of tricky thing here is I'm using a zero-sum normal distribution, which constrains the sum to 0, if you can't tell from the name. But it's helpful here because we're never going to want to like predict for another team. So it's OK to have that constraint in the model. And then the age GP. So one thing I didn't mention is that the exponentiated quadratic is way too smooth. And in practice, your default choice should be a Matern 5.2, which is the one in the middle. And these pictures probably look pretty similar, but the fact that it has to be so smooth means it won't fit a lot of data. So you may not believe it, but oftentimes, if you're sampling a model with the exponentiated quadratic or fitting something in a different library, like it won't work with the exponentiated quadratic, but then you switch it to a Matern 5.2 and everything's fine. So that's a nice trick to know. Your default should just be a Matern 5.2 and then go from there. And I'm not going to put the formula up because it's like complicated. And that's why all the examples you'll see use exponential quadratic, is it just because it has a simple form. So the length scale prior I end up using is a PC prior. And because I want to allow I want to allow for there to be no age effect in the model. So if I used an inverse gamma, I'd be forcing there to be an age effect and kind of would feel like I'm stacking the deck a little bit, which, as we learned, you shouldn't do. So the PC prior is good for, it weights that space, that visual space, equally as the length scale increases. So the two parameters you have to set then are the lower threshold, the lower cutoff, so the resolution of your data. So for this, I picked 5 years, and then the probability that it could be lower than that, so 2.5%. And that's sort of, so I'm sort of forcing there to be a slower curve over age because I don't think it's going to do this, right? You could think there's going to be an age peak and then a decline. So you have to include as much information as you can. So copy paste this away to use a PC prior. It's kind of complicated looking. And we're planning on including this in PyMC extras, so you can just like use it without doing that. And here's the result you get after you do all that stuff. And If you don't do all that stuff, this is not the result you get. But what you can see here is that, so this is the posterior of the GP age term in the model. And the age actually really does peak exactly at 26, which is interesting, and drops off and then gets really uncertain because out here, because there's very few pro baseball players with these ages. So yeah, and so why did we use a GP for this again? So we had no idea what the functional form was for the age curve. We sort of had a vague idea that it would be smooth and peak in someone's 20s maybe. But if you had to design a parametric function, maybe you'd reach for something like polynomials or splines, but that would probably work fine in this case, but you'd have to think carefully about the number of components or the degree of the spline and all that sort of stuff. And you'd have to make choices and do model selection, perhaps, if you're being very careful. But in this sense, GPs are a lot easier to use, as long as you know how to deal with the length scale prior. It's really that simple. And yeah, unlike parametric functions, GPs can extrapolate outside the bounds of their data too, in a sane way. So yeah, this is to wrap it up. We started with a very quick intro to Bayesian modeling and then showed how GPs are an extension of hierarchical models, and then talked about why setting the prior on the length scale is critical, how to do it, what to watch out for. Also talked a tiny little bit about PyMC and PyTensor, which is great. And the short answer is to really be as informative as possible and think about it. And so, I hope you can use this as a resource to be more comfortable with using GPs in your model. And then thank you. And any questions?
Yeah, we're on time, so we have time for 1 or 2 questions if anybody has something to ask.
Okay, thank you. You said it's like not to stack the deck, but I guess you tried different priors and then picked whatever curve you liked better. How to find that balance between stacking the deck and doing the right thing?
I think for GPs, the space of functions that the length scale, even that one parameter, and I didn't even talk about the fact that you can add covariance functions. You can make very, very complicated ones. But the amount of functions that fill that space is really huge. And so when you're changing the length scale, you're sort of just changing the smoothness that you're allowing, but not where it's going to go. So in that sense, you're not stacking the deck, but yeah, it is kind of a weird balance of trying some stuff your model doesn't fit. This always happens, right? And then re-examining your priors. And I think the right way to think about it is to think of, oh, I ran this thing, it didn't work. Well, maybe I actually know a little more than I thought I did. And then you can update your prior with that. Does that kind of answer? Oh, thanks, yeah.
Yeah, I had a quick question, and this is going to be, I'm going to be digging into my back a little bit, but if I'm remembering correctly, covariance has a bit of a sensitivity to scale. So do you have to do any preparation to your data before you jump in and do GPs, like divide everything by 1,000 or whatever,
You don't have to. It's helpful. When I'm doing stuff, I won't standardize right off the bat or anything like that. But if all your numbers are in thousands, like thousands of dollars, they're in dollars, but all the numbers are thousands, I'll just divide them by 1,000. Just to keep it in sane areas, but so that it still has a unit that's understandable, which helps with setting priors and stuff like that. So, yeah. So your answer is kinda. Yeah. Thank you guys for staying.